So, let us conclude the course on transform techniques for engineers. In this course we have learnt how to find some transform techniques. In this course we have learnt Fourier series and Fourier transform, Laplace transform and Z transforms. So, for periodic signals, that is functions over a finite domains, we have Fourier series as a inverse transform, Fourier coefficients which you can define as a sum infinite, Fourier coefficients as your Fourier transform. So, we have defined Fourier transform, inverse transform as a Fourier series, so that when you have a periodic signal you can represent this as an infinite series. So, that is your Fourier series. Based on this we have derived Fourier integral theorem formally, and also rigorously we have derived this Fourier integral theorem, but provided the signal that f of x defined that should be smooth domain, that is not just for continuous function. Continuous function you cannot have a Fourier series, it should be a smooth function. That means it should be differentiable wherever it is continuous. Just continuous function, you have seen that there is no such function for which you have examples in the literature that just continuous function which is not differentiable, you cannot have a Fourier series that is finite, that converges. Okay. So, but you have seen many examples piecewise continuous functions. You may think that this is not continuous. Okay. It is continuous, but every piece wherever it is continuous you have a piecewise you have a function, that signal is smooth, that means it is differentiable within the wherever it is continuous, and you can allow finitely many discontinuous jump discontinuities in your function or signal. Okay. So, based on this we have derived Fourier transform, different versions of Fourier transforms, and we have learnt how to find the Fourier transform and inverse Fourier transforms, and then and it is based on its properties. We have given a lot of properties based on which we have derived how to find the inverse transforms, inverse Fourier transform, and then we made use of this Fourier transform to find to solve some differential equations, to solve some integral equations, and we have seen other applications how to evaluate certain integrals. Okay. We have seen this in this course, and also based on again Fourier integral theorem, we extended the class of functions for which this Fourier integral theorem is validity. We enhanced the validity of this Fourier integral theorem. So, you end up getting Laplace transform from the Fourier integral theorem. So, that means based on the Fourier integral theorem we ended up getting Laplace transform and its inverse transform, but the only thing is we paid a price here, that is it is not you do not have a domain anymore over the real line, you are spilled over to complex plane. So, you have to deal with complex integrals. So, you have Laplace transform is an integral over 0 to infinity, but your inverse transform is basically in the complex plane. So, that is the price you paid by extending the class of functions for which you have Fourier integral theorem is valid. Okay. So, they are all interlinked, all these transforms are interlinked so far, and again we explain how to find these Fourier Laplace transforms for simple functions, and then we derived certain properties. Based on these properties you can get this inverse Laplace transform. For general function you have seen how to evaluate those contour integration techniques you can apply. You can use these contour integration techniques to find the inverse transform, and then you use these Laplace transform in the applications. For example, you can solve ordinary differential equations, partial differential equations with initial, especially when you have the initial boundary conditions both are provided for your partial differential equations. You normally use this Laplace transform technique. It is because for that is why we use this Laplace transform technique to solve hyperbolic equations, that is a wave equation, and parabolic equations. A typical equation is heat equation. So, that is where you have time is involved. So, you have an initial value you can provide. So, but you cannot use this for the steady state heat equation, that is elliptic equation or a Laplace equation as an example. So, we cannot use this because of this if you have to provide only boundary conditions. If you provide only boundary conditions, you will not have when you apply the Laplace transform, you need the initial value set either of the variable we use. For example, if you apply Laplace transform to uxx, you need u at 0 y and ux at 0 y. So, both these things are required, but if you provide any of these two, and you may end up the problem the boundary value problem is not stable. Stable means we will just give an example of a Hadamard example. You can see this example in this slide. Hadamard's example is when you solve this Laplace equation in this upper of plane, this is upper of plane, what you have only boundary is this minus infinity infinity, at which if you provide initial value at y equal to 0 is this, and uy if you provide, clearly for this problem, and 0 is one solution, clear, right. When you have 0, you can easily see that 0 is one solution. Okay. For example, if you provide let us say u of x0 is 0, okay, and u of uy x0 equal to 0. You take 0 condition here, 0 0 here. If you take, let us take uxx plus uyy equal to 0, x belongs to R, y positive. So, this problem has a 0 solution. So, solution here is 0, u of xy is completely 0, identically 0. Okay. This is one. Now, if you consider, if I change this initial data, for example, the second initial data that I give sin nx by n, if you take n very big value, then sin nx by n is very small quantity. So, that means I give a little perturbance in this initial data, and if you give such an initial data sufficiently big n, what happens? This problem has a solution here, 1 by n square sin nx into sin hyperbolic ny. So, if n is sufficiently big, n square is growth is smaller than sin hyperbolic ny, because it is exponential growth e power ny plus e power minus ny divided by 2, that is your sin hyperbolic. So, as n goes to infinity, n is sufficiently big, this solution is away from 0. So, as you see, we give the initial condition as sufficiently big n, this quantity is very close to the initial condition of this problem. So, these are very close, but the solutions are not very close, okay. But as n goes to infinity, these two deviate from each other. So, that means the solution is not depending on the initial data continuously. The solution is not continuously depending on the initial data. So, that is why we do not solve this initial values we do not provide to this Laplace equation. So, assume that one of this data is you can think of as unknown. As an unknown, you keep it, and then you provide you using the boundary data whatever you have, you apply the Laplace transform, and you may end up at the end you try to whatever you get the solution, that using that solution you can get your you can apply this other initial condition to see it may work. So, you can apply such technique. That means you have if you apply if you have a boundary value problem for the Laplace equation, try to apply Laplace transform to one of the variables, and you need another initial data, that is for example ux or uy at x0, uy at x0 or ux at 0 y, okay, that you do not know, because you have to provide only only boundary data for the Laplace equation, because it is elliptic type. So, you assume that whatever is requirement after applying the Laplace transform, you call this some general function as an unknown function, okay. Let us call this some c of x, and you as though you know everything. So, you apply everything. The only thing is that you may not be using all the boundary data in your if you apply the Laplace transform. So, in that case, whatever you have not used, you try to apply at the end and try to get this unknown function cx, which is the initial data uy at x equal to 0. If you call this as cx, which you assume, you can get this unknown function, arbitrary function cx, from one of the boundary data that you have not used. So, you can apply that technique may work or may not work. Okay. So, we do not normally, that is the reason we do not normally use Laplace transform for the boundary value problems alone. So, you need, if you have a initial boundary value problems, this technique is very useful to solve some partial differential equations. Okay. So, that is what we have seen in the Laplace transform applications, and we have in the communication theory you have signals that are discrete signals. We normally report, we have plenty of data that is discrete type. So, you can apply the signal processing technique to get this discrete transform that is similar to the Laplace transform. So, it is called a Z transform. Again we derived based on only Z definitions of Laplace transform and its inverse transform. You get Z transform and its inverse transforms, and again we proved for all different sequences, discrete signal is nothing but sequence data, that is for different sequences we have derived Z transforms, and also it is how to find and we gave some properties to find the inverse Z transform, and then we applied Z transforms to solve some differential equation, discretized version of differential equations that are those are difference equations. So, you can solve this these difference equations with initial data by Z transform technique. Also another example, we have evaluated certain infinite sums involving a parameter using these Z transforms with the additional properties that we have provided in the last video of this course. Okay. So, with this we have learnt different types of continuous and discrete transform techniques and their applications that are useful for most of engineering and physical sciences. Thank you for watching.